Hello and welcome to another physics lesson. The purpose of this particular video is to take a look at the gravity problems 2, which I've noticed a lot of people have been having difficulty with. This is a problem set that kind of combines uniform circular motion with Newton's law of gravity. And at the time of this recording, I think the best grade anyone has is a 4 out of 12. So clearly people are struggling, and I've gotten several emails with questions on this one as well. So I'm going to try to do just one video. This is a short video. This is the only board I have for this, so hopefully it'll be pretty quick. So let's just get into it and see if I can get you guys on the right track with this assignment. So here's our basic setup. We have something orbiting a planet. Now the idea here is that if there wasn't for the force of gravity, this would follow a straight line path. But because of gravity, it falls from that straight line path. Now if it doesn't have enough speed, it will fall and crash into the planet. Now if it has a little bit more speed, it'll go a little bit farther before it crashes. But if we give it just enough speed, then it will fall around the Earth. You can see there's a straight line path. It falls below that straight line path towards the planet, just like any other falling object. But because its speed is great enough, it never actually gets closer to whatever object it's orbiting. We can imagine that this is Earth or the Sun or whatever. And so we sometimes say it's falling around instead of falling into. And so here it would be the straight line path when it gets to this point. And again, it's falling below that straight line path. And so with the right velocity, it can continue to do that. And so part of this assignment is to look at, well, what is that velocity? How do I find it? What affects that velocity? Now, obviously, it's moving in a circle, so centripetal or circular motion is going to come into play here. But the other thing to recognize is that the only force acting on the object is gravity. And so gravity comes into this. So we're going to look at those two equations, and we're going to try to combine those equations. That's the point behind the first question on the assignment. Now, I'm not going to do all of it, but I'm going to show you how to get started on it. In fact, you should have got this equation on part 1 of the gravity problems, but in case you didn't, we'll kind of go through it. So you start with the Newton's law of gravity, that the force of gravity is a gravitational constant times the mass times the product of the two masses divided by the radius squared. In this case, I've changed it to be the mass of our planet and then the mass of our satellite, just so we're kind of clear on which mass we're dealing with here later in the problem. Now, because it is in free fall, the only force acting on it is gravity, so my net force is equal to the force of gravity. I'm getting ahead of myself. We also know second law is net force equals ma. And so in this case, we're looking for the mass of the satellite, and we're looking for the acceleration of the satellite. So we're dealing with the satellite here, because we're interested in what's its velocity. So that's where we are with that. And so I combine these two equations, and I can cancel the mass of the satellite. It's in both equations. And so then we can see that the acceleration of the satellite as it orbits Earth depends only, or whatever planet it is, depends only on the mass of the planet and the radius of that orbital path. Logically, we can see then if I go to the acceleration, the centripetal acceleration of that object, we know centripetal acceleration depends on the velocity and the radius. And so these two things, and since the acceleration doesn't depend on the mass of the object, then logically the acceleration or the velocity isn't going to end up depending on the mass of my object either. It's only going to depend on radial distance and the mass of the planet. So any object, I mean, we've already seen this. We've already seen that all objects have the same acceleration when gravity is the only thing acting on them. We've proven it multiple different ways in class. So it's true for an orbiting object too. It doesn't matter the mass of the satellite. If I put it at a certain distance, it's going to have a certain acceleration. And what we're seeing here is going to have a certain velocity. All I have to know is where I want to put it and around in the mass of the planet I want to put it around. So the other thing that you might need to use then is just finding the velocity of that object as it follows around. So I have gotten an email about that. And we can do it using, if you combine these equations, you get that master equation. Maybe you have the information to use that. But we can also just use good old classic kinematics. In which case we're just saying, hey, the speed of an object is the distance traveled divided by time. In this case, the distance is a circular path. That's circumference. That's 2 pi r. And then we ask for the time. Again, to get all our units to match, we need that time to be in seconds. So it could be a lot of seconds. If we're talking about the Earth orbiting the Sun, that's 365 days. We'd have to convert that to seconds. All right. I hope that helps you on these problems. Please keep emailing me if you have questions, and take care.